Welcome to This Explainer. Today, we're going to look at some R code, but we're absolutely not going to just read it like a textbook. Instead, we're going to treat this code like a physical machine. We're building a mathematical engine right inside R to solve a massive, real-world transportation puzzle. Okay, let's dive into this. Imagine the headache of trying to move thousands of tons of wood from multiple source locations to entirely different markets. You've got trains, you've got ships, and each path has a completely different cost. Plus, some paths aren't even possible by water. So how do you do this without wasting a single dollar? Well, you don't guess. You use math to literally guarantee the absolute lowest cost. And that brings us to our magic number for today, 15. This represents the total number of unique routes we have to juggle simultaneously in our logistical puzzle. Now, keeping track of 1 or 2 routes is a breeze, but 15 interconnected routes with varying costs and strict limits? Yeah, that requires a serious system. To demystify this intimidating block of R script, here is our blueprint for today. We'll start with the multimodal logistics puzzle, initialize the LP model, map it with nested loops, build the objective function, define the model constraints, and finally, optimize the shipping plan. Let's get to it. Section 1. The Multimodal Logistics Puzzle. Before we write a single line of code, we really have to understand the shape of the physical world we're trying to model. We live in a two-dimensional reality here. We've got 3 sources of wood on the left. See those numbers in parentheses? That's our strict supply limit. Source 1 has 15 units, source 2 has 20, and so on. Across the top, we've got 5 markets with exact demand requirements. When you cross-reference those 3 sources with the 5 markets, you get the grid you see here. That's 15 distinct potential routes. It's a classic 2D matrix, which is exactly how our brains naturally visualize the problem. Moving on to Section 2, initializing the LP model. Now we need to actually build the engine block. We do this using the elp solve package in R. We kick things off with this specific function, make.elp. It takes 2 arguments. The first is the number of rows, or constraints, which we set to 0 for now because we haven't built our guardrails yet. The second argument is the number of columns, which is our sources multiplied by our markets. 3 times 5 is 15. So we're basically telling R to set up 15 columns. The absolutely crucial point here is that each of these 15 columns represents a decision variable. It's like a blank puzzle piece. We are asking the model to decide exactly how much wood to push down each specific path. It's an unknown quantity right now, but trust me, by the end of the script, the model will assign a precise number to every single one of these variables to perfectly balance our costs. Section 3. Mapping with nested loops. Okay, here's where the heavy lifting really happens. I like to think of this as the engine's pistons. The major challenge is that the ElpSolve package doesn't understand 2D grids. It literally only speaks in straight 1D lines. So we use nested loops to flatten our map. The outer loop locks in source I. Then the inner loop fires, iterating through markets J from 1 to 5. Once it hits market 5, the outer loop clicks to source 2. And we repeat. It completely unrolls the map into a single line. And to keep track of where everything goes, we use this brilliant little math formula. I minus 1 times the number of markets plus J. Let's actually test that 2D to 1D magic. Say we're looking at source 2, market 1. So I is 2 and J is 1. 2 minus 1 is 1. 1 times 5 markets is 5. 5 plus J, which is 1, equals 6. The code perfectly drops the shipping cost for that specific route into the exact 6th slot of our 1D vector. It flawlessly flattens our 2D world into a 1D line. Section 4. Building the objective function. With our loops acting as the gears perfectly mapping everything out, we can now build the steering wheel, the objective function. We tell the model our ultimate goal is to minimize total cost. Now, while option 1 represents a really basic model that just blindly assigns fixed rail costs, option 3 is where the magic happens. It acts dynamically. It creates a smart decision engine right inside our nested loop, comparing rail versus shipped costs on the fly to find the absolute minimum for every single route. Let's break down exactly how smart this option 3 loop really is. For all 15 routes, the code first checks if water transport is even possible using an is.NA check. If it's NA, it instantly defaults to the rail cost. But if a ship route is feasible, it does some math. It takes the shipping cost, adds a 10% ship investment cost, and then hits the min function. This is the brain. It literally pits the rail cost against the total ship cost, mathematically selects the cheaper option, and only then assigns that winning minimum cost to our 1D objective vector. Section 5. Defining the model constraints. Because an engine without guardrails is just going to crash, right? A model without constraints will give you impossible answers, like shipping 1,000,000 tons of wood for free. Look at how the loops generate this beautiful binary map of ones and zeros to communicate with LP-Solve. The top row is source 1's supply limit. Notice how only variables 1 through 5 have a 1? That tells the model the sum of those routes cannot exceed source 1's supply. The second row is a demand constraint for market 1. Variables 1, 6, and 11 have a 1, effectively telling the model that wood coming from all three sources to market 1 must perfectly equal its demand. It's such an elegant way to lock physical reality right into our math. And finally, Section 6, optimizing the shipping plan. We've built the engine block, mapped the routes, installed the dynamic steering wheel, and bolted on the guardrails. Now we turn the key. We pass our model into the solve command and let the math find that perfect balance. By calling getObjective, the model spits out the truly optimized multimodal shipping plan. It tells us exactly how many units go on which train or which ship, route by route, proving our nested loop math successfully optimized the whole system without breaking a single rule. The logic we just went through isn't just for wood, trains, and ships. It's a fundamental framework for efficiency. So as we wrap up this explainer, I want you to think about your own data. Whether you're shifting employee schedules, routing server traffic, or managing massive supply chains, how could you build a mathematical engine like this to solve your own complex logistical headaches? Because once you know how to flatten the board, the math can solve almost anything. Keep learning, keep building, and I'll see you on the next one.